Hi, I'm Alison Ord. I'm going to talk today about a view Bruce Hobbs and I have been developing over some years now of orogenic gold deposits as nonlinear systems. This talk is focused on the nonlinear analysis of data. The approach is non-parametric and is completely data-driven so that the raw data speak for themselves. We aim to discover the underlying dynamics of the system. We need to understand the cross-correlations between the mineral concentrations produced by the interconnected processes that develop the mineral system. Mineralising processes are multiscale and nonlinear. Patterns of alteration and mineralisation are apparently irregular and unpredictable. As examples, we see here mineralisation imposed on fracturing, imposed on alteration at the LNDO mine in Chile, and varying cerussite composition in drill core. This drill core is from the Sunrise Dam gold deposit. The deposit is hosted in shear zones, and a typical alteration assemblage is quartz, calcite, dolomite, anchorite, paragonite, muscovite. Chlorite is common, presumably inherited from early metamorphism of mafic and sedimentary host rocks. The ore body is characterized by its complexity in gold grade distribution, which typically is nuggety, erratic, and difficult to estimate. In order to demonstrate the principles involved in the nonlinear analysis of a mineralized system, we use hyperspectral and gold assay mineralogical data from this drill core. Here are plots of the raw data with depth down to 500 meters sampled at half-meter intervals. Figures A, B, C, and E show the abundances of calcite, dolomite, anchorite, cerussite, and chlorite, respectively, as established from infrared absorbance in the near-infrared. The abundance scales are arbitrary, so that relative proportions cannot be read from these figures. Figure D is the variation of the absorbance wavelength in nanometers of white micas along the drill hole. The chemical composition of the white mica can be established from this plot, with aluminium poor and silicon rich phengites at wavelengths greater than 2200 nanometers and aluminium rich and silicon poor muscovites and paragonites at wavelengths less than 200 nanometers. Figure F is the distribution of the logarithm of the gold concentration in part per million by weight established by assay along the drill hole. Let us look now at recurrence. The recurrence of states being again arbitrarily close after some time of divergence, is a fundamental property of deterministic dynamical systems and is typical for nonlinear or chaotic systems. How do we measure recurrence? Let us first look at the sine wave, start at P. Clearly there is a recurrence, a place of the same value every half wavelength. Start at Q. Clearly there is a recurrence, which is regular but not every half wavelength. Here we look at the construction of a recurrence plot for a sine wave. Take a point A on the signal and plot all points that recur. This gives us A1, A2, A3. Do the same for another point B, giving B1, B2, B3, and repeat for any other point X. The result is a series of diagonal lines with the vertical spacing equal to the period of the signal. Here we look at the signal on the top left from the Lorentz system. B shows the attractor for the system. The system en masse is either convecting clockwise, for example, with a greater than 0 value, or anti-clockwise, perhaps with a less than 0 value of the signal. The recurrence plot is shown in the right-hand figure, showing that the vertical distance between diagonal lines is a measure of recurrence, and that vertical lines represent chaotic transitions. A recurrence plot identifies recurrences at different parts of the same signal on the one attractor. Here we see recurrence plots for these data. They're all for an embedding dimension of 10 and a delay of 5. Black represents near zero recurrence, blue high recurrence, and green intermediate recurrence. Long diagonal lines indicate similar phase space behavior of the signal. That is, the length of the diagonal line is a measure of how often the trajectories of the system visit the same phase space regions. They are a measure of determinism in the system behavior. The lengths of vertical or horizontal lines are a measure of how long the system remains near the same state in phase space. These lines are commonly referred to as chaotic transitions and mark changes in the behavior of the system. All plots show strong chaotic transitions, the horizontal and vertical lines, although precise correlations of these transitions are not obvious from one plot to another. The presence of these transitions distinguishes these signals from white noise, so there is clearly structure in the system. Strong determinism, diagonal lines, is patchily developed, particularly in the plots for cerussite composition and gold concentration. A cross-recurrence plot identifies recurrences at neighboring places in phase space for two different signals. It identifies those places where state in one system recurs in the other. If the phase space trajectories visit different regions of the phase space, the cross-recurrence plot tends to sparse. Simultaneous occurrence of similar states produces dense plots. Here are cross-recurrence plots for gold versus cerussite by composition, cerussite, chlorite, calcite, and dolomite. Or the cross-recurrence plot shows some degree of synchronization between the gold concentration and the other mineral species. The strongest correlation over the broadest range is between gold and cerussite composition. The most diffuse correlation is between gold concentration and cerussite abundance. The correlations become localized between gold and chlorite, gold and calcite, and gold and dolomite anchorite, with the most localized correlation between gold and dolomite anchorite. These plots indicate that the spatial distributions of all mineral species are part of the same system, but that the depositional process for gold is strongly related to chlorite alteration and the deposition of carbonates, particularly dolomite anchorite. The relationship between gold concentration and cerussite abundance is perhaps incidental, but there are strong cross-correlations between gold concentration and cerussite composition. So cross-recurrence analysis shows strong spatial correlations of gold with carbonates and weaker correlations with the phengitic micas and chlorite. Now we explore joint recurrence plots, which portray the probability that two systems recur simultaneously in the neighborhood of a formerly visited point in their respective phase space. Here are the joint recurrence plots for gold versus cerussite by composition, cerussite, chlorite, calcite, and dolomite. The joint recurrence plots for gold concentration with the other mineral species are very similar and all resemble the recurrence plot for gold concentration by itself. Thus, although all the raw signals and the recurrence plots are different, the joint recurrence plots are very similar. This means that both the densely and sparsely occupied regions on the gold concentration recurrence plot tend to be mutually reinforced by states on the respective recurrence plots for all the other mineral species. Thus, there is coherence in the system, in that there is a high probability that all signals recur simultaneously in phase space. It seems that although all the signals are diverse in character, they are all part of the same system and the coupling strength between all the subsystems is relatively high. So joint recurrence analysis reveals all parts of the system are part of the same dynamical attractor and hence parts of the same physical chemical system. The nonlinear analysis highlights that the essential characteristic of the incoming fluid is it has a chemical composition capable of strong chemical reaction with the host rocks. The presence of gold in solution is of course necessary, but incidental to the operation of the system. The chemical reactions with the host rocks are strongly exothermic and generate a varying EH-pH environment responsible for gold deposition. Autocatalytic reactions associated with quartz and carbonate deposition control pH variations responsible for gold deposition. The heat generated by such reactions drives the deposition of quartz and carbonates and again incidentally gold in such a way that all the reaction deposition processes, including oscillations in EH-pH, are strongly correlated, comprising a unified coupled dynamical system. The data are best fit by the specialized extreme value distributions, including Frechet, Weibull, and Gumbel. The data are less well fit by the heavy-tailed distributions of Pareto, Cauchy, Levy, and the long and heavy-tailed log-normal distribution. These estimated distributions for the data arise from the underlying dynamics for the system. In the present big data environment, where huge data sets are routinely collected in the minerals industry, it is important to extract as much knowledge from such data as possible. Recurrence analysis is a method for rapidly extracting knowledge from these large, expensive data sets and for providing fingerprints to quantitatively characterize and compare data sets. Thank you, and have fun recurring.